So let me give you some examples as to how these predictive matrices can be used to determine which areas of the product or the application will be faulty. So these are some of the information gathered from across the industry or from our daily experience of producing the different applications. So let me talk about some of the matrices in the requirements or design phase. So completeness of requirements, they generally are a good predictor of fault proneness. So from our experience, we have seen that incomplete requirements are like a major factor of producing faulty products and causing customer dissatisfaction. By the way, a lot of the defects that are captured in the LM process actually generate from the requirements management phase. In fact, the percentage is more than 50%. Then the volatility or stability of the requirements also impact or also predict that the final outcome will be stable or not. So if the requirement is being worked upon, the version is changing regularly until the day you are releasing it for QA, then it can be assumed that the code that has been written to implement this requirement also has got a lot of churn. It has been checked in multiple number of times. Something was done, again removed, again something else was introduced. As and when the requirements are changing, the coding is also changing to support them. And this is a typical scenario which produces a lot of defects. Then design defect density also predicts how faulty your application will be, because the design, as it is very much higher up in the workflow, so if you have a lot of defects in the design and they were corrected multiple number of times, most probably your final application is going to be quite faulty. Then also the complexity of design, the data flow complexity, is also one of the predictors of fault proneness of the final product. So the more complex the design and the data flow, you can expect that the number of defects discovered over the life cycle of the project will be much more. Looking at the metrics that are used in coding, so one of them is the static analysis matrices. So when we do static analysis and we get to see that one particular class or a module or maybe a particular developer, whatever code he or she is writing, is failing in the static analysis, producing a lot of problems, then that is going to be a predictor that this particular module is going to produce a lot of defects. Then the cyclomatic complexity of the classes, the higher the complexity, there are chances of producing more bugs or defects in those areas. Depth of inheritance is also another measure in the coding stage that that can predict that if you have a long depth or a very deep inheritance, then there are chances that some of the cases are not handled and it might produce defects. And code churn is another one that I said that the number of times a particular code has been changed and modified and reworked on, chances of producing a higher defect density is high. So these numbers are not like absolute numbers and that have a very linear relation with the number of defects produced. So there are in between these matrices and the prediction, in between that there are some models that are used or for predicting this behavior. So these are mostly statistical and probabilistic models that are used. So I'll have a short discussion on that in the next slide. And predictive metrics in testing, of course, code coverage is a good indicator that if your test cases are covering only 40% of the code, then the remaining 60%, when it falls in the hands of your customer, it's going to produce some defects. So these are some of the different predictive models that are used in the industry to come up with the target numbers, and I will not be going into the details of each of the different models. So these are basically dedicated subjects of study by themselves. So discriminant analysis is mostly like you are changing some of the parameters and how it's going to affect different parts of your product. Classification trees are based on types, how you are classifying your modules and your defects. Bayesian belief network, or popularly known as BBN, is also a probabilistic model. Then another one is constructive quality modeling for defect density prediction. This is also used to predict the number of defects in the final product and accordingly make changes now so that it can come down. Then Rayleigh curve is a model used for predicting the defect discovery. So at which stage how many defects are going to be discovered. And so this is very funny in the sense that say you are not discovering as many defects. According to the curve, you are supposed to get say 50 defects in a particular time frame, and you see that you have got only 5. So that is a red signal for you that your testing is not happening properly. Otherwise, at this stage, it should have produced more defects. So these are the different relationships that occur between the existing numbers, the current numbers today, and what it is predicted to do when the final product is delivered. Then multivariable linear regression. So these are done by changing the values of more than one variables and seeing that how it is going to impact the final product, and based on that these variables numbers are matched to the actual numbers that are coming up from your code development, application development, and if they are not matching, then the corrective actions can be taken at that stage. And of course, Monte Carlo simulation can also be done on the requirements part, where the volatility and overlap of requirements, these parameters can be modified to see a what-if scenario that if we change the volatility to some number below the current one, how is it going to impact my final quality. So these are some of the predictive models used today.